Hello, everyone. First of all, I am very happy to welcome one of my best friends as today's speaker. Utku got his PhD degree in physics from Istanbul Technical University almost a year ago. And since the last year, he has been a postdoctoral researcher at Boğaziçi University. And he has expertise in, I think, many areas, especially in mathematical physics, like supergravity. And I can also add that he has developed his expertise in how to be a good father as well. And okay, today we will talk about his latest paper, which is about Carrollian and Non-relativistic Jackiw-Teitelboim Supergravity.
Thank you very much, Eda, for this very nice introduction. Also, thank you. I would like to thank to the organizers for giving me this opportunity to talk about my recent work. And today I'm going to talk about the Carrollian and Non-relativistic Jackiw-Teitelboim Supergravity. It is two different limits of JT supergravity. So it's based on the paper with me and Lucrecia Rivera. So let me start by giving you a brief outline of my talk. So I will start with some features of two dimensions, and then I will start by giving you an introduction to JT gravity, and then I will discuss the background field formalism of JT gravity, which will be our starting point. And then I will consider JT supergravity as a BF theory. And along the way, I will give some very brief summary of BF theory structure. And then after this discussion, I will give a brief summary of supersymmetric extension of non-relativistic JT gravity. And the last part of my talk, I will cover this ultra-relativistic so-called Carrollian JT supergravity. At the conclusion, if we have enough time, I will mention some feature works So let's get started. By the way, if you have any questions, please feel free to interrupt me at any time. So let me give you a very brief overview about a two-dimension. Actually, two-dimension is very interesting because so suppose our goal is to obtain an interesting models of gravity at lower dimension, especially in two-dimension. So the simplest examples you might think of is the Einstein-Hibert action. But that one is the topological in two dimension. In mathematical speaking, it gives us Euler characteristic. So then you might think, let's add matter to this action for obtaining an interesting model. But it fails because in two dimension, when you externalize this action with respect to metric, you get Einstein tensor, but Einstein tensor is 0 in two dimension because, as you know, in two dimension, Riemann tensor, also rigid tensor, completely fixed by the rigid scalar. So if you know the rigid scalar, you know everything about the local geometry. So it is not enough for our construction because every metric in two dimension is a solution of the Einstein tensor, but it's 0. So if you want to focus on some sort of very specific metric, say ADS or DS, it is not enough. So we need another model, and this is the Jackiw-Teitelboim gravity. So we can do it by considering different coupling to the matter sector. And as you can see, an answer to this question is the JT gravity in two dimension. Here you can see we introduce an additional scalar field and it couples to gravity in this way. And as usual, lambda is the cosmological constant. In this context, I will consider just negative cosmological constant because we are considering the supersymmetric extension of this model. So if I define this model,
sorry, I just missed. Why we need another model? You said, I think, but I missed that.
Yes, because in 2-dimension, for instance, we have gravity theory, we have Einstein-Hibert action in 2-dimension. We have Einstein-Hibert action for gravity. It works very nicely in 4-dimension. When you extremize it, you get Einstein tensor, and it also you get some vacuum solution, for instance, Schwarzschild, and also Kerr black hole solution, etc. And also, I mean, you can single out some of the solutions. For instance, these are the Ricci flat solutions. But let's say Einstein-Hilbert action is also works in 2-dimension. But in this context, you can see by varying the Einstein equation, Einstein-Hilbert action, you get G mu equals to 0. So this is identically 0. Whatever.
So Utku, may I ask you? So you said that any solution of Einstein's equation is the vacuum solution in 2 dimensions. Is it correct?
No, I mean any solution is the solution of the Einstein tensor. G mu equals to 0. The every solution of the 2-dimension.
So they are all vacuum.
Sorry.
So they are all vacuum solutions, no?
Actually, I'm not sure how to call it, but if you, for instance, in 4-dimension, the vacuum solution corresponds to the R mu. The Ricci tensor is the 0. In this context, we have G mu is 0. Whatever, no matter you have matter field or not, because the G mu is identically 0. It is 0 for every metric. For instance, if you put some arbitrary metric in 2-dimension, its G mu is 0. So, for instance, if you want to consider just ADS, 2-dimension ADS metric, you have to find a field equation that enforces us to say, yes, we are in a manifold with constant curvature. So because this is the result of the properties of the Riemann tensor, because in 2-dimension everything is fixed by rigid scalar. So in this context, also Einstein-Hilbert action is just Euler characteristics. It gives me some number for a given manifold. So as I said, every metric is solution of the Einstein tensor, but I want to obtain very specific one, so it is not enough. It allows me, it does not allow me to obtain, for instance, ADS case. But let me go to the JT case, and things will be clear enough. Let's see. For instance, if you take this action, apart from the Einstein-Hilbert action, you get, by varying with respect to scalar field, you get R minus 2 lambda equals to 0. So this equation says me you have a manifold with constant curvature. Directly, this fixes the geometry. So if you vary the action with respect to the metric, you get equation of motion for the scalar field. So let me briefly summarize the dynamics of the model. Classical equation of motions are given in the following. So first one is obtained by the varying with respect to the scalar field, and second one is as I said, in 2-dimension, Riemann tensor is completely fixed by rigid tensor. So if you know the rigid tensor, you know everything about the local geometry. So you can see the equation of motion of the metric gives me the last equation of motion. So this is, in this equation, one might think that this can be considered as a back reaction of the scalar field to the geometry. In this context, I neglect the boundary term, but if you consider boundary term with the JT gravity, you get some Schwarzschild action at the boundary. So you can see this is not pure ADS. So that's why they call in the literature this is nearly ADS space-time. But as I said, I will neglect the boundary term from now on. So there are several motivations to study JT gravity. So let me summarize some of them. Firstly, you get JT model by direct dimensional reduction of 3-dimensional Einstein-Hilbert action plus cosmological constant. Also, you can also obtain JT gravity, or its modification by dimensional reduction of 4D gravity theory. For instance, Einstein-Maxwell theory if you do the dimension reduction, you get JT gravity. So secondly, JT gravity appears as a near horizon effective theory of near extremal higher dimensional black holes. For instance, if you take the Reissner-Nestron metric, if you zoom in onto the horizon, you get ADS2 cross some compact manifold. So if you want to consider the dynamics of the near horizon geometry, you need to consider JT and other 2D dilaton gravity. So another motivation to study JT gravity is that. And also the boundary action of the JT gravity is Schwarzschild action, and it is dual to it is the low energy limit of SYK model. So it is, I'm not very familiar with this model, but it is studied in the context of condensed matter systems. So we can say that this is another toy model for holography. And finally, black hole information paradox, because black hole information paradox has been a long-standing puzzle in the study of black holes. By using JT gravity and its black hole solution, you can obtain some page curves. I mean, so there are a lot of papers about this issues and this black hole information paradox. So these are the motivation of the JT gravity. So, but in this talk, I will consider and the BF theory formation of the JT gravity. It will be our starting point for constructing supersymmetric actions. So let me briefly summarize briefly mention about the BF theory. In a sense, it has some feature as the Chern-Simons theory. It is convenient to consider BF formulation to construct supersymmetric and other extension of the JT gravity. So if Lie algebra admits non-degenerate, symmetric, and invariant bilinear form, you can construct these BF theories. You can see this GLK is our killing form or bilinear form metric, and we have some structure constants, and also we have some generators here. You can see that this theory is invariant under the following gauge symmetries, and also you can obtain the field equations. You can see from the bottom line. So this will be our starting point. Let us construct the JT gravity as a BF theory. First, I will introduce. I'm going to introduce the ADS2 algebra.
May I ask a question? What is X? So there is this A, right? It is a gauge theory. But what is X here? X
is in this context somehow in the JT gravity context, it is dilaton field, it is a scalar, or in this context we call it Lagrange multipliers. So in the JT, the X will be our scalar field somehow by solving the equation of motion. We will see in a moment. So the first order formulation of JT gravity in BF formulation basically can be constructed by gauging the ADS2 algebra. You can see the the commutator of the ADS2 algebra. J is Lorentz generator, PA our translation symmetry generator, and the lambda is lambda is the cosmological constant. As I said, we are considering the negative cosmological constant in this context. So this algebra admits invariant, non-degenerate, and symmetric metric. So as you can see, we said if you have some kind of metric structure here, it is different than the metric of the spacetime. It is metric of the algebra. If you have this kind of metric, you can construct the JT gravity as a BF theory. So if you have Lie algebra and you can associate the gauge fields to the each generators, and you can see from the equation 1. So the first one is Zweibein and second one spin connection, and correspondingly you can write your Lagrange multipliers with these generators. So also you can see we can construct by using the algebra, we can construct curvature 2 forms. here. And using these curvature 2 forms and the Lagrange multiply, we construct BF theory formulation of the JT gravity. You can see from the equation 3. So let me say something about this. So if you vary the action with respect to XA, you get RP equals to 0 here. So RP is equals to 0 is a Cartan structure equation, and it allows us to solve the spin connection in terms of Zweibein. So if you plug into the action, you get exactly same action here, JT in the second order formulation. Also, if you vary with respect to the X, you get Einstein equation of motion. So this is the BF formulation of the JT gravity in the equation of motion.
May I ask a question? Maybe just because I don't understand. So the thing is that, I mean, so you said that the Jackiw-Teitelboim gravity is the no. So okay, so in 2 dimensions it is not Jackiw-Teitelboim, right? It is just the usual gravity is topological, but JT gravity is not, right? It is not topological. Yes. Sorry. This is my bad. Okay. Sorry.
Okay, let's go to the supersymmetric extension of the ADS2 algebra, because this will be really our starting point to construct the Carrollian and Non-relativistic supergravity action. So ADS2 algebra can be extended with this ADS2 superalgebra can be written in this form. So you can see we have 2 kind of supersymmetry generator here, because of course you can construct n equals to 1 JT supergravity, but in our context we use the n equals to 2, and it will be clear in a moment. So using this algebra, we can construct again invariant bilinear forms. You can see from the equation 6. So this one is the R generator, but they are bosonic, and this is my fermionic metric. So you can construct JT supergravity action like this. You can see that the first line is just bosonic part, and this is the this comes from the R symmetry, and also we have this fermionic part. Also, the lambdas are the same as the X and Xi. It is Lagrange multipliers, and I indicates the number of supercharges. So from now on, I will use this action as a starting point to construct a Carrollian and non-relativistic supergravity action. So we will use the Lie algebra expansion methodology. And first, you should, if you want to use the Lie algebra expansion, you should decompose your Lorentz indices like this. You can see we split the space-time translation in this way, and our gamma matrices. Also, we need to introduce following combination of fermionic generators to do very convenient to do the expansion. And then, if you plug this splitting into our algebra, you get pre-expansion algebra, so it will be our starting point, and then we can consider the following expansion, which you can see from this line. So I expand P0 H plus n square m, etc. So this expansion, after using this expansion, and if you plug this expansion to the relativistic algebra, you get non-relativistic algebra, so-called Newton-Hooke algebra, the supersymmetric Newton-Hooke algebra, where eta is the some expansion parameter, because we are not considering the contraction, we are using the expansion in this context. As you know, I think you know, we have three kind of methodology to obtain new algebras, Lie algebras. First one is the just univariate contraction. Second one is the extension of the algebra, and third one is the Lie algebra expansion. Why Lie algebra expansion is very convenient in this context is you get the more symmetry generator, because contraction preserves the number of generator, but we need more of them because of the invariant bilinear form. I mean, in order to have a non-degenerate invariant symmetric bilinear form, you need to expand your algebra. So this will be our starting point. And then by using this expansion, we get the following non-degenerate invariant metric for Newton-Hooke superalgebra. And our gauge fields can be expanded like this. You can see from this line. So this is the gauge fields of the extended Newton-Hooke algebra, which means non-realistic superalgebra in 2 dimensions. So we can use this construction, this non-degenerate metric, and this gauge fields, and we can construct our action like this. We use very interesting labels for them, but anyway, so by using this metric, we can construct this JT action. This action is a supersymmetric generalization of the bosonic one. It appears last year in 2 papers. So this one, the non-relativistic JT supergravity action. So after this point, if you have any question, we can stop here, and then or I can continue the discussion. Now we finished our.
I have some question. If I understand right, your aim is to construct a new algebra for GT supergravity by using some extension models.
But non-relativistic algebra. Not relative. Yes.
Okay, to investigate what? It's my question. Why you want to construct some non-relativistic algebra?
Yes, very good question. Actually,
I mean, behind the physical motivation, what's this?
Yes, you are right. As I said, this JT gravity is somehow very useful toy model for investigating some of the nice features of, I mean, geometries, boundary actions, etc. So it is very natural to investigate another sector of the JT gravity, which is non-relativistic sector, because it will be interesting to consider somehow the non-realistic boundary actions, and it may correspond to some different condensed matter systems, as I said, or it can also dwell to some another limit of SYK model. So that's why we are investigating the other sectors of this JT gravity. For instance, non-realistic or Carrollian, and of course, mathematically speaking, it is just mathematical curiosity to investigate this another limits of this JT supergravity action. So, as I said,
okay. Utku, may I ask you? So, why do you supersymmetrize in the first place? So, then a similar question to Eda's question. So, why do you make it supersymmetric?
Actually, because it's absent, so we did it. the first way, but I'm joking, by the way. Actually, it is true for relativistic cases, not only non-relativistic cases, but supersymmetry somehow enables us to consider or to construct some fully symmetric theories. For instance, I mean, or you can say that you can do some link with the superstring theory, not directly this JT gravity, but we know we have some kind of string theory. It's supersymmetric and supersymmetric string theory. So so supersymmetry is very important in this context. Also, as I know from the relativistic cases, also this can also enable us to consider some integrable systems. I'm not sure, by the way. As I said, this is just the construction, and not focusing on its application. Maybe the bosonic sector is just enough for the construction. So that's my very naive answer to this question. I mean, it is also true for relativistic cases. So maybe we can discuss later. So we have this JT supergravity action, non-relativistic JT supergravity action. Then we can construct ultra-relativistic Carrollian one, and ultra-relativistic Carrollian JT supergravity can be obtained by just consider the following map. You can see from this picture. You can also, of course, use the Lie algebra expansion, or you can use this duality map. So this duality also enables us to consider to go from non-relativistic to Carrollian cases. So if you do this map to action and the algebra, also the non-relativistic metric, you end up with the Carrollian JT supergravity. There is a duality, but of course you can do expansion. In this case, you can expand your fermionic generator like this. Also, you can expand your the generators of the algebra in this form. And if you extend, if you plug this into the relativistic ADS2 algebra, you get extended ADS Carroll superalgebra, and and this algebra admits the following invariant bilinear form. So you can construct ultra-relativistic JT supergravity by using this construction, and this is the ultra-relativistic JT supergravity action as a metric BF theory, and based on the extended ADS Carroll superalgebra. So this action also supersymmetric generalization of the bosonic Carrollian JT action. So the supersymmetric extension of non-relativistic and ultra-relativistic JT gravity, let me give some very brief summary. This we consider the supersymmetric extension of JT and ultra-relativistic JT gravity. So you can see the duality is preserved in the action level. For instance, you can start from the action, you can expand the gauge fields and the curvatures. You get the same Carrollian and also Newton-Hooke algebra. Also, you can go from Newton-Hooke non-relativistic JT supergravity to the Carrollian one by using this map directly by expanding the action. So as you can see, there is an even and odd structure of the expansion of fermionic and the bosonic algebra. Let me briefly give. You can see we expand P0 odd number of eta here and P1 even number of eta. But in the non-relativistic case, we expand P0 even number of the eta, P1 odd number of the eta. This structure of the expansion determines our Carrollian or non-relativistic Newton-Hooke algebras. So, okay, let me comment on some feature works. So BF theories, you can use this beyond BF theories and construct beyond the supersymmetric Newton-Hooke and ADS Carrollian models. I mean, you can use the methodology that we constructed in this paper. You can obtain next order actions, maybe they, and also you can also use this Lie algebra expansion to consider Schwarzian actions, boundary actions. Also, you can use this expansion that we introduced in this study, in this work. You can construct supersymmetric extension Carrollian and Non-relativistic boundary actions. Also, you can use this expansion. I'm not sure, but you can use this expansion to consider other deformation of JT gravity, because JT gravity is one of the dilaton models. There are many two-dimensional dilaton models, but in this context, we use the JT be a formulation of JT gravity. So I think I cover everything.
May I ask you one question? So you say that these boundary actions. So what do you mean by this boundary action? So you are working in this two-dimensional space, no? I mean, then your boundaries. So you mean that one-dimensional Schwarzian action, or your theory corresponds to some boundary action in two dimensions. So what do you mean by this boundary Schwarzian?
Very nice question. Actually, the boundary action corresponds, for instance, in the ADS case, because we are in the ADS space-time, the boundary is the time-like. So at the boundary, we have just time direction. And this Schwarzian somehow corresponds to, as I know, this Schwarzian action corresponds to the Gibbons-Hawking-York term of the JT gravity. Let me show again. You can see I neglect the boundary term, and you can add some boundary term here, which is Gibbons-Hawking-York term, and if you calculate, it corresponds to the Schwarzian action. But in this context, I neglect, and it is so it is just one-dimensional on the time-dimensional theory. You are right, because the boundaries in ADS case, boundaries time-like. In DS is boundaries space-like, but we are using the ADS cases, so it's boundaries time-like boundary. I'm not sure I give your
No, I think it's perfectly fine. So for me, thank you.
If you have any question, we can talk, but thank you for your attention.
But I need to go. Öyle bir şey mi diyeceksiniz? But I need to go.
For this nice and very quick presentation, Utku.
Thank you very much.
Thank you very much.
Are there any other questions? Because we have enough time to finish this. But
I thought, actually, I thought it will be nice to give a talk, a very short talk, and I don't want to give all the details of the calculation because it's not important. So because I want to give some general overview about this non-realistic and the Lie algebra expansion and how to obtain this non-realistic algebras and ultra-realistic algebras. So how to consider this different type of JT supergravity actions.
is there any meaning of this pictures? I'm not sure about this, but maybe you.
I wanted to ask about it.
Actually, this I take it's from the paper of Maldacena. It was about this boundary action. So if you say, yes, we have ADS spacetime, but because of the dilaton field, because of the back reaction, your ADS spacetime becomes nearly ADS spacetime, and you have to carve out the boundary. So the Schwarzian action, that the action Mahmut asked about it. So the boundary action is the theory of this this winging of the boundaries. So it corresponds to the Schwarzian action. If you have perfectly ADS spacetime, it's fine. You get the left hand side, but in this context, the boundary of the JT is somehow this.
Deform the geometry.
Yes, deform the geometry. So that's why we have this Schwarzian boundary action in the JT gravity, the JT gravity. So.
And they thought that, okay, in this subject would be scary and we can choose a bet. Okay, I don't know, because it's not very nice.
I should change my presentation and this picture for you. Next time I find another very interesting picture for.
Okay, if there are any other question, we can.
By the way, I think yes, there Lucretia is here. If you have other questions, maybe she can answer.
Hi Utku and hi all. Hi.
Because I was very when I saw the Lucretia and say, oh, okay, everything's fine, because when you ask some hard question, Lucretia can help me. So
Okay, fortunately we couldn't have any hard question because we are not experts on this issue.
So maybe I have one question. Is related like to your I think third or fourth slide, when you were talking about the setting of the theory, the JT theory. At some point you have mentioned this fact about two-dimensional manifolds and the fact that you can, you can reduce the problem and everything is determined by the Ricci scalar in that case. So I was wondering, I mean, is there any in let's say higher dimensional manifolds, do you have some kind of condition under which you can, let's say, transform your metric in such a way that the Ricci scalar is constant throughout the manifold?
actually, it's in 4 dimension you have constant curvature in, for instance, ADS space in 4 dimension, as I understand correctly. So you can have the 4 dimension, 3 dimension ADS space time, and their rigid tensor is rigid scalar is constant in this context.
So if you start from let's say a general metric, then you can see this as I mean, can you transform this metric in such a way that the Ricci scalar can you always do this in such a way that your Ricci scalar is constant throughout the
in 2 dimension, you mean?
No, I mean in general dimension. What is known about this this kind? I think this problem has a name, right? It's something known in geometry, I guess.
Actually, I'm not sure I understand you perfectly, but in 2 dimension, you can bring the metric always conformally flat dimension, but I'm not sure for higher dimensional cases. So in 2 dimension, you can bring your metric conformal flat cases. So that's why we said the Einstein-Hibert action is just Euler characteristic number, but I'm not sure for the other higher dimensional cases. So
I don't know, maybe Ayman, can you say something about this?
Yeah, I understood that you are referring to Yamabe problem. But your question is, can we always refer, because it's about what kind of transformation you want to make on the metric. So for Yamabe problem is to say that there is a conformal metric that provide the solution for constant scalar curvature. I'm not so sure if your question is go beyond that or.
No, I mean, I only wanted to say that as far as I know, in general dimension, this is an open problem, right?
The open problem, do you mean transforming?
Problem, yeah. Using a conformal transformation of coordinates.
No, actually, it's already solved. So it's not an open problem. It's a solved problem. we know that for sure that we can do this as long as, yeah, there is some condition about the Yamabe number. It should be strictly less than the Yamabe number of the sphere. There is some condition that you have always some maximal value for because this problem you can write it as some variational problem, and you can construct some number which is the infimum of of some quantity. And we know that as long as we have some strict inequality, we have the Yamabe problem is solved. So we are sure that there is a conformal metric, which is where the which provide that the scalar curvature is constant. So this is what I know related to this. And,
okay, no, thanks for the clarification.
You're welcome.
Okay, if there's any other question, we can thank again Utku for this talk, and I hope we will meet next week for another physics talk.
Thank you very much.
Thank you, Utku, again, and
Thank you. Thank you for the
have a
talk.
good day.
Thank you.
Have a nice day for everyone.
Thank you very much.
Thank you.